Hi, my name is Jeff Denworth. I'm Chief Marketing Officer and a co-founder of Vast Data. And now we're really excited to take the covers off of the Vast Database. The Vast Database is essentially a critical component of the Vast Data platform, and it really allows us to apply the contextual or semantic layer into the system such that as we're going and refining data through the data platform and working with this very rich forms of unstructured data, we can now apply a semantic understanding of that data in both transactional context, meaning we can receive flows of data in real time, but also in analytical context so that we can really go and process on that data and analyze that data in real time as it's flowing through the system. It's really important to understand our design principles when we build the different technologies that come together in the Vast Data platform. First is embracing standards. We want to build systems where you can bring your applications to the data, and that starts by having open interfaces that enterprises can trust and are familiar with using. So today, with respect to the database, we're going to be talking about SQL. We'll also be talking about Apache Arrow and how that can influence the connection with other query engines that the Vast Database is designed to work with. We also embrace the idea that we really want to simplify every single aspect of the approach to infrastructure that we're bringing to the table. And first, getting rid of different complex tiers of data management, and also really finding first principle solutions to working with customers on how they most want to work and the simplest ways to deal with their data. And third, as with everything we do, it's really about allowing you to deploy infrastructure on your terms. Your data, the clouds and either public cloud or private cloud that you want to deploy on, is entirely of your choosing. And with the Vast Data space, now we can stitch all of this together into one unified environment where everything is always under your control. So first, we wanted to build a system that essentially allowed for us to build the contextual layer on top of the data store. The Vast Database allows for all of the data in the system to basically be streamed in real time and also cataloged in real time using the Vast Database. So it's a transactional system, first and foremost, that's designed to organize your data, but it's also analytical in the sense that you can quickly understand everything that's inside of the system. Secondarily, the objective here is to really simplify the way that people do data engineering. In the data science space today, people typically wrestle with things like how to manage their semi-structured data objects and how they deal with these in the data science context. And we're basically eliminating all of these constraints in a new approach to building databases that we're super excited to introduce today. To understand a little bit about what we've done, we wanted to take a step back and first explain how we think about the database management system market. Classically, within most organizations, you'll find a collection of systems that are designed to deploy and manage tabular data or tables. And so starts by having databases that are typically used to transact data into. These are online transaction processing systems. And this is essentially systems that are designed for very high speed ingestion of records within your environment. Those systems typically don't scale, and for that reason, customers then go and build other systems to analyze their data that gets to much larger data sets. And typically those are data warehouses or data lakes where your data gets deployed into as you start to go and build structure on top of some semi-structured objects like Parquet or JSON that you may be familiar with. Now, when we started, we kind of asked the question, why do all these systems exist? And if a database was fully featured such that you could scale to any level of proportions and you could query upon the systems that you're also transacting to, would we have all of these technologies in the market today? And that answer is probably no. But in order to understand how to remove the constraints that have resulted in these different types of systems, we wanted to really think about, okay, why are these different technologies in play today? And first and foremost, it starts with the on-disk representation of data. You think about the dichotomy between databases and data warehouses. Databases are designed to capture data in record form. But then to do deep queries upon your data, you want to essentially organize your tabular data into columns. And when you get down to the storage level, typically that's a very different style of storage that's required to handle both of these two operations. On one hand, you're dealing with IOPS and very, very small IOs. On the other hand, you're looking at data through a different lens and streaming in large IO dimensions. Forever, these have always been two different styles of storage that are used to serve these different purposes. Next, if you think about building to scale and really wanting to analyze all of your data, scalable systems anymore are largely built with the classic shared nothing architecture that we reviewed in the days section. And Days solves for a lot of these problems, and we'll talk about that in a moment. But without that, what you have is a series of direct attached storage nodes that are typically being used for data lakes and data warehouses. And the challenge becomes you can't use these systems also as transactional platforms for reasons that all of the nodes need to then talk to each other during transactional events. And transactions that have interdependencies result in serialization. Serialization results in bottlenecks that people typically can't deal with. And at the end of the day, you transact into a database and you read and query your data in a data warehouse. And then finally, as you start to think about really, really scalable infrastructure, as best as we can tell, the market really hasn't digested the idea that you should use Flash for all of your data. Vast, for the last 4 years, has been spending a lot of effort and a lot of time democratizing the use of Flash all the way down to the archive. And until then, customers are largely stuck on hard drives for their large data lakes, which really doesn't work for people that want to go and transact into environments using rapid I/O, IOPS-centric operations that are classic with databases. And so for this reason, you've always had different types of systems in an environment. If we take a step back and we think about the challenge around solving deep analytics with real-time infrastructure, we started to think and look at the different data platforms that are in the marketplace today. And a lot of them advertise support for low-cost cloud storage. And the promise of these products is that you just get all the data that you need as far as you can scale, and everything's really simple. But then as you kind of poke into these architectures and these products a little more, what you'll see is that all of them are dependent upon some level of acceleration that comes in the form of caching. So most data lake technologies now have different cache layers that you put on top of it, ultimately to mask and avoid the challenges that come with querying data that sits in low-cost cloud or on-premises object storage. And so the hard drive is still playing the villain in this story by really limiting customers to get real-time access all the way down to the archive. There we find some challenges that definitely can be solved with a modern architecture. So as we started to dig a little bit deeper into how different data platforms dealt with the topic of analytics, what we saw is that data engineers spend a lot of time dealing with how they size their different partitions that they put into their data lakes, typically using file formats such as Parquet. And in this case, you really have no easy recipe that is in play as you start to think about how to manage your data within these environments. Engineers are wrestling with how to size their files either big or small to solve certain objectives. If you go really big, you get great compression on your data, and you also get the ability to relieve pressure on your metadata servers. But on the flip side, that creates a lot of challenges when it comes to query engine efficiency, because the more that you have in your file size, the more that you ultimately have to go process through in your query at your query engine layer. Let's make the files really small. That's a great idea, except for the fact that you lose all of the compression benefit that you got by making your files big. And at the same time, a high proliferation of files in your environment puts a ton of pressure on your metadata store. Now, on top of that, when we started to look at different customers, what we realized is that every data lake format essentially looks to go and version all of the data that sits in your data lake. And versioning is a complicated topic when it comes to dealing with updates to data. And if you have really big files, then if you want to just update a few records or delete a few records within that file, you have to go rewrite the entire Parquet file that you created. And so a few kilobytes of updates can result in many gigabytes of data that has to be rewritten. And so even if you have small files, that problem still prevails. You just have less data to rewrite. When we started to think about what the requirements were of this system that could essentially break the constructs of the batch paradigm that essentially, starts to marry closer to how the human brain works, we wanted to build a system that as data comes in through the different senses, files, objects, tables, streams, essentially we could go and make realizations upon this data in real time. Here we had to essentially cross the boundaries between event-driven architectures where data comes in and there's action taken, and data-driven architectures that historically you would use to do batch processing and analytics on your data. And what we wanted to build was a system that could ingest data at very, very high rates of speed in a transactional manner, but at the same time query upon that data instantaneously in a real-time data-driven manner. And that's the essential component to basically building a system that reacts with data events on the fly. And for this reason, we needed to invent an all-new approach to database services that we call the vast database. The vast database is essentially intended to do is to blur the lines between database services, data warehouse services, data lake services. Imagine a system that is a system of record, meaning that it can handle transactions at very high levels of scale, but at the same time allows you to query on all of your data instantaneously all the way down to the archive. That makes it also a system of insight. In order to do this, we needed to bring a ton of invention to the table. So let's build beyond and think about something new. Now, it's important to understand that the database starts by building on top of the vast DAYS architecture. DAYS stands for disaggregated and shared everything. And what we have is a next-generation distributed system where all of the logic runs in standard Linux containers, just stateless cores that are essentially running all of the processes of this system, all the functions. And then over a high-speed, low-latency data center fabric, all of the data is presented to all of the machines in parallel in one global volume of low-cost flash. Really what we've done is we've abstracted a cluster architecture and made essentially a data center scale computer where you just have cores that all have access to the same global volume. And that is instrumental to rethinking the whole database paradigm, because if you don't have machines that need to coordinate with each other at all in the read or write path, then you can start to build for very, very transactional services, but at the same time get to unprecedented levels of scale, both in terms of capacity and in terms of performance. Now, one of the critical aspects of the DAYS architecture is a write buffer that we build into storage class memory that's much, much larger than standard system write caches can be. And so this buffer essentially builds a shock absorber on top of the system that allows the system the luxury of time to manipulate data before it's flowed down into low-cost flash. And so in the case of the database, it really provides a transformational service for the system in that we can receive data in standard database record form. We can transact to persistent memory as a database would typically work. Using storage class memory, that's the fastest persistent media that we have access to today, and the machine can be very fast. As the buffer starts to fill up, there's a background process that will ultimately migrate data that sits on the buffer down to very low-cost flash. Historically, that process of migration involves us basically manipulating data as we want it to take down to its final resting space. So you can imagine the system's doing data reduction and encryption and data protection. And what we've done with the vast database is also installed a process that allows us to transform records into a columnar data format that ultimately gets laid down onto low-cost flash. Now, the interesting thing here is if you think about building a database in 2023, would you build that off of hard drives? Of course not. And what we realize is that the same principles can also be applied to data warehouses and data lakes. As we start to build for large scale, meaning petabyte to hundreds of petabyte systems, VAST has solved for the problem of flash such that you can afford flash for all of your active data. And once we've done that, it makes zero sense to use hard drive-based constructs in terms of how we lay data down onto disk for your analytics environment. Here, we built a new style of columnar object. And here, it's about 32 kilobytes in size, which, if you're counting, is roughly 4,000 times smaller than your standard Parquet row group that you'd otherwise put in your data lake. 4,000 times smaller, you can just get to an incredible level of filtration for your queries. And it's not about moving different query services down into the vast data platform and accelerating them. It's also about doing more with less resources. And so at 32 kilobytes, when you ask a question or you query into the system, it goes down and gets precisely the data that you want and only the data that you want in these little small 32 kilobyte atomic objects. And so the system can be extremely fast, particularly for fine-grained operations because of the way that we lay data down onto disk. With this object is also things like footer data, and here we put things like min-max values and counts. It looks a lot like a standard Parquet file. But at 32 kilobytes, then you've got something that's much smaller, and we organize all of these different columnar objects in the system using our metastore, where we can build sorts and projections and filters on top of your data, such that it's really easy to go and query through. And when you compare the two, there's a quote in Saving Private Ryan that one of the actors talks about finding needles in stacks of needles. And that's really the way that I think about the vast database. When you're dealing with data in such a fine level of granularity, then when a query hits the system, it's so much more efficient in terms of the storage utilization than anything that's come before it. Now, when I started the session, I talked a little bit about SQL. SQL is one of the presentations of the system that you can go and write natively into the vast database with and query from. But we also have built pushdown plugins so that you can support other popular query engines and accelerate them using the vast database. And so here we've already built plugins for Apache Spark, as well as Trino and the different derivatives of Trino that are in the market. We're adding Dremio right now, and we'll add other different popular query engine support in the future. And what you get with this is pretty much anything that you need with respect to your data infrastructure that sits underneath of these query engines. So a metastore, a database, a catalog, all of the policies, all the security controls that you want to put on your data on a system that it can extend from edge to cloud. Remember, one of the key objectives of the DAYS architecture is to build a system that can be transactional at scale. When you think about that applied to a database convention, then what happens is you now have a system that you can just add cores to, and it gets linearly faster as you keep growing the system. Add CPUs, add GPUs to the system, it gets faster. Add SSDs to the system, it gets bigger, and the SSDs also make all your data activities faster. So how does it look when you start to scale it up? Well, we just take an example architecture, and let's build a crazy large system, like 100 petabytes. At 2-to-1, you get roughly a system that has about 1 million transactions per second that you get out of this infrastructure. So very, very, very transactional, as we've alluded to earlier. But at the same time, you get about 5 terabytes a second of sustained streaming performance for your queries. And so now you have no boundaries between where your capacity is and where your performance is. We've brought that all together in the vast data platform. One of the things that data engineers typically toil over, as I mentioned earlier, is the challenges with respect to sizing your partitions or your Parquet files and really working towards the right mix of performance around those files and the reduction that you get through local compression that typically gets implemented on a file-by-file basis. Here, this is where VAST has brought some really interesting innovation. The DAYS architecture supports a new form of data reduction that we call Similarity. And Similarity is not compression, nor is it deduplication, but essentially you could think of this as a modern form of global compression. As data rolls through the system, we're leveraging the write buffer to take a little bit of time to look at the data before it ultimately gets flowed down to low-cost flash. And one of the things that we're looking for as we're fingerprinting on a block basis is opportunities to find similar blocks in the system. They don't have to be exactly the same like a deduplication engine would work. When we find two blocks that look similar enough to each other, what we do is we compress them together using a compression algorithm that comes from Facebook called Z-standard. This pattern matching can go all the way across the entirety of the data store, across all your files, all your objects, all your tables, and really has no boundaries in terms of the scale of the implementation. But the granularity that we look for patterns goes all the way down to just 2 bytes. And so imagine if you were able to zip up the entirety of your entire data center, or at least the entirety of your data lake, and just compress everything together as one big compacted object. That's ultimately what happens with Similarity. Now, when you want to go read from the system, reads are happening in real time, and decompression is electrically pretty much free. So everything happens within less than a millisecond, even though you get global reduction across all your tables, your files, and your objects. So when we apply that to the infrastructure, building on the fact that we also have extremely efficient error correction algorithms that we've implemented, we call these locally decodable codes, building on the fact that we support the lowest cost forms of flash that typically enterprise systems weren't designed to work with. When we put that all together, what you get is a system that transforms the ownership calculus of all flash data lakes. And as we compare that to other popular products in the marketplace, what we see is that the vast database typically comes in anywhere between 5 to 10 times less the cost of modern solutions that would otherwise be flash-based. And the objective here is to democratize flash for all of your data such that you don't need to make choices about what data you want access to in real time and what data you are okay with accessing in kind of a more archival fashion. If you get that all out of the equation and you just build your entirety of your data store on flash, if you think about both big data as well as machine learning applications, essentially all just applied statistics. And if you can expose these algorithms to the most data that they can possibly get their hands on, you've got the best possible statistical accuracy that you can bring to the table. As we compare this to other popular data platforms that also support data warehouse services, what we realize is that there's a number of advantages that the DAYS architecture and the innovations that we're building into the database bring to the table. And so, of course, you can do pre-planned and well-organized queries, but by taking Flash all the way to the archive, it's really suitable for ad hoc queries. It's great for transactions, not just for a single table, but you can transact across as many tables as you want to in an ACID fashion and never worry about the limitations from a performance perspective with the system. It's great for IoT data, it's great for real-time streaming data, and it's also great for analytics that go all the way down to the archive. Now, we built the system with an ETL that allows you to put in data like, let's say, Parquet files. You drop those into an S3 bucket, and we'll transform those into our columnar format. We also support the import of data through the different plugins that we've built, so you can import data using things like Apache Spark or Trino. The other critical implication here is that it's also embedded into a file and object storage system. And so not only does that provide a basis for cataloging all of your data, and Andy talked about our vast data store, which is our file and object system, and how the database is now applied as a catalog for your data. But if you think about modern deep learning pipelines, you have both the need for very structured data systems like databases and data warehouses, but you also have the need to support the different types of data representations that Python developers like working with, such as file and object formats. So we brought that all together into a unified system, so it's the most comprehensive approach to basically all of your data science. And then finally, where do you deploy it? It's not just offered in the cloud as a cloud service, but you can deploy it on premises, and you can stitch together both all of your clouds and all of your on-premises data centers into a unified view of all of your table data using the vast data space. Now remember, we've been shipping for about 4 years, and we started shipping the vast data store. And if you think about a storage system, a lot of the same properties of a storage system equally apply to database services. And so here we get to bring a whole litany of features to the table that customers expect, and you typically don't get from a first version of a database product. And that includes all sorts of different capabilities like data encryption, snapshots that go across all of your tables, so you get time travel. We have support for audit functions. We have support for all sorts of access policy management and a number of other technologies that typically you would expect to come in versions 2 or versions 3 of a database product that's hitting the market for the first time. And that's the story. The vast database is transforming how people think about database management services. It's a wildly scalable architecture that combines transactional and analytical capabilities into a single system where you don't have to worry about where your data is anymore. The analytical capabilities take deep analytics all the way down to the archive. And what we're delivering is a revolutionary level of data reduction so that you don't have to worry about the costs associated with taking flash all the way to the archive, and an uncompromising level of resilience so that it can be both a trusted system of record and system of insight for the modern enterprise. Thank you.